guys, we are doing magnetism creating electricity. Key concepts we are covering is right-hand rule, Faraday's law, Lenz's law, self-induced voltage, LR circuits, and LC circuits. First, the right-hand rule. To use the right-hand rule, you want your fingers in the direction of the velocity, bend them in the direction of the magnetic field, and you want your thumb in the direction of the current. Faraday's law. The rate of change of magnetic flux produces an electromagnetic field. Picture.
Lenz's law says that the induced EMF and the induced current are in directions that oppose the change that opposes them. So basically, this means that if there is a current, then Lenz's law says that there will be an opposite current that is induced by the induced voltage that will do the opposite of what that first current does. And that's why the current oscillates in a sine wave in LC circuits. So this is an example when the field is getting smaller, and we can use the right-hand rule to show the direction of the induced current. So to see what direction the current is, you bend your hands in the direction inside of the paper since the X's are in the inside, and then you can see that the current is going clockwise. Self-induced voltage, the induction of a voltage in a current carrying wire when the current in the wire itself is changing. That is the inductance. And the formula for this is E is equal to negative L times di over dt, which is the rate of change of the current.
Okay, so now we have our LR circuit, which is when there's an inductor and a resistor. So here are two graphs we want to remember. So when we're turning on so I of t is going to be increasing, and then di over dt of t is going to be a decreasing slope. So here is our little table to remember our formulas. You also want to remember that VR plus VL equals 0. And then you guys can read the rest of the table, but basically you want to remember that the pattern 2/3, 1/3, 2/3, and 1/3 for T equals L over R. And then for turning off, it's going to be for I of t, it's going to be a decreasing, and then di over dt of t is going to be increasing below the x-axis. And then for this table, here are all the equations, and remember that VR is equal to negative VL. And then for T equals L over R, it's all 1/3 times whatever the equation for T equals 0 is, and then the pattern positive, negative for the 1/3.
So now we have our LC circuit, and you can see the inductor and the capacitor in this drawing. So with an inductor, we use the formula U equals Li squared, and U is the maximum amount of energy. And then for a capacitor, it's a similar formula, but this is Q squared over 2C to find the maximum amount of energy. And the use of conservation of energy is used here because the amount of potential and kinetic energy is going to be the same. And then the relation between the inductor and the capacitor using the period is this formula on the bottom right. So that's how you find the capacitance or the inductance using the period. And then with an LC circuit, we also have a sine wave here, except due to Lenz's and Faraday's laws, it oscillates. And so it reaches the maximum amount at intervals of 1/4 t. So like 1/4 t and then 3/4 t, and then zeros at like half t. This is our lab, and this is when we generated electricity using different magnets. So for this lab, we used magnets with 6 turned all the way in, 6 alternating, and then 12 turned all the way in, and then 12 alternating. And the red line that you see on the top is actually the 12 alternating, and that shows that the maximum amount of magnetism causes the max amount of electricity. So this is our this is our multiple choice question. And as you can see, the answer is 0.78. Okay, so we used V equals the rate of change of the flux. And then that, as you know, is equal to the magnetic field times the area. And then if you just keep simplifying that, you eventually get to BL times dx over dt. And that's because the length stays the same, but the velocity of the x direction changes 2.6, as you saw in the question. And then as soon as you put those in, you're going to get the answer 0.78 volts.
For our next multiple choice question, for trying to basically find what happens when the loop of wire moves into the region with the magnetic fields. So the answer is D. And basically, Lenz's law denote that because the magnetic flux is increasing when it's moving into it, so it's going to create the electric fields. And then because there's an electric field, there's obviously going to be a current. And we know that the current has to be in the opposite direction of this increasing flux due to Lenz's law. So if it's in the opposite direction, then it's going to slow down. Or free response question. So a square of loop wire with a resistance R and a side length of S is placed in a uniform time-varying magnetic field, and the magnetic field is given as negative B naught cosine omega t, and omega is a constant. And so basically, we're just trying to answer parts A, B, and C. So for part A, derive an expression for the magnitude. We're going to want to remember our equation. So E equals the velocity times the length times the magnetic field. And then we have our knowns is the resistor equals R. And then we also know from Ohm's law that E equals IR. So basically what we're doing is we know that the change in flux is the area times the change in the magnetic field, in the magnetic flux. So we have the area, which is S squared, which is the sides, obviously because it's square, so just the side lengths. And then you have the negative B omega sine omega t, because you're going to integrate your magnetic field. And then for B, derive the expression for power. So we know power is voltage times current. And then you just go through a variety of you're just manipulating the formula, and we eventually get the EMF squared over the resistance. So, and we already found the EMF in the Bell equation, so you just divide it by R. And then for C, you're finding the net force on the loop. We know that force is the integral of I of the cross product of B. So you integrate it to get IL cross product B, and then you just put in all your known values, and that's how you get there. Okay.
Okay, so now we're going to do parts D through F. And so for part D, it asks for a graph from t equals 0 to t equals t. And here, as we said before, the graph of the current is a sine wave, but because this gives us the formula for the magnitude, it's going to be positive throughout the whole entire domain. So that's why our graph looks like that. And then it is clockwise, the direction of the current is clockwise because t is positive at 1/4. And then for part F, to find the charge, we are going to use I equals V over R, and then take the integral from t equals 0 to t equals 1/4 and then multiply that by dt to get the total amount of charge, because the charge is equal to the current times time.
That's all you guys need to know for magnetism creating electricity.
Have fun studying!